Okay, guys, we're going to go through the cyclotron now. The cyclotron is a form of particle accelerator that works on some very simple principles involving magnetic and electric fields. Here's an example of a layout, obviously taken apart, a cyclotron. You have magnets on top and bottom, so you have a magnetic field running either, in this instance, down, or if you switch the polarity, it could be up. All right, you have this part in the middle is very important. These are what we refer to as the 2Ds. They are evacuated hollow chambers that particles can move through. Evacuated, so in a vacuum, so they don't involve collisions. If you're trying to accelerate something, particularly a charged particle, you don't want it to collide with other particles. It will lose its energy and it will lose its charge. Okay. Now, the general story of what's going on here is the particle will start off in the middle. So there's a little spot here, sometimes referred to as the ion source. From there, it will be accelerated to one of the sides of the Ds, and then the magnetic field will cause it to rotate around. Basically, it will keep performing semicircles. So as the magnetic field turns it around, it will come back between the Ds, and so on and so forth. But you also notice that they're spiraling outwards. What's happening between the Ds is there is electric field. There is a magnetic field throughout that's causing them to go through in a circular path. But every time the charged particle accelerates through the Ds, it will be accelerated by the electric field. Now, you may ask, okay, well, if you move from left to right and you get accelerated, won't you decelerate as you move from right to left? The brilliance of this design is they have a alternating current source. And it's actually very simple because we'll pick up a couple of equations that we've actually used already. All right, the first one involves the relationship between the radius of the circular path of the charged particle in a magnetic field and its velocity. Obviously, M and Q are properties of the charged particle. B is the magnetic field strength. And you notice that R and V are directly proportional. So basically, if R doubles, V doubles. Now, we used this before to come up with this formula for the periods, the period being the time to complete a circular orbit in a magnetic field. Okay, now you notice that this formula is completely independent on velocity and radius. So it takes the same amount of time to complete a circular path if it has low energy, low velocity, or high energy, high velocity. So the time it takes for it to come back through the Ds is consistent. Now, period also has a relationship with frequency. So we're talking about this alternating current. Just think about that. Okay, well, frequency, oopsies. Okay, just find myself a bit of space. All right. All right. So we know that period is 2 pi m on QB. Now, what's frequency? In relationship to period, frequency is the number of oscillations per second, and period is the time in seconds for one oscillation. So in that case, the relationship between frequency and period, F frequency equals 1 on period, thereby F equals, according to this, QB on 2 pi m. So that is also an equation, it's a more or less the same equation, where it is independent of the speed and the radius of the charged particle. So this is the one that you set your alternating current to. You set your frequency around the parameters of the particle you wish to accelerate. And that particle will likely be a nucleus of some variety, like a proton, alpha particle, maybe lithium, or if you're doing the experimental work, maybe something much heavier. If you're making radioisotopes, it's probably going to be something small. And we'll come back to that in another lesson. So we're just going to go through the this device for now, the cyclotron. Okay, so you have a constant frequency which enables So as the charged particle accelerates from left to right, and then it gets turned around, comes back right to left, and is also accelerated because the direction of the electric field is now switched. So it switches right to left, then left to right, and so on and so forth. So the charged particle is always accelerated. So every time it passes through the D's, it will gain kinetic energy. And let's go back to our electric field concept. So electric fields, it will gain delta K. Every pass, it will gain the kinetic energy of the potential difference times by the charge. So if it completes a full circle, it will gain 2 of these, 2VQ. All right. Now, we would like to know how much energy, what would be the final kinetic energy of this? Now, there's a couple of things we have to be that will factor into this. One is actually the size of the device. There's a number of features that will determine the maximum energy that you can get out of this, or actually the energy. If you evacuate the chamber, the charged particle will just keep spiraling hours and hours and hours until it's gained enough energy to be guided out, as you can see here. There's an end where the charged particle is guided out, and then it moves in a straight line after that, not affected by any more fields, until it strikes a target and does what it's needed to do. Okay, so if you made this, made the D's larger and made the whole device larger, it could complete more spirals theoretically, and thereby reach a higher energy. So one of the variables we're going to need is R. So maybe just put that into our diagram. We'll just draw a little. We're going to draw a little thing, and we'll call that radius. That's going to be R. All right. So it's R max. Okay, but this equation I'm about to derive could actually be used for any point along the journey in terms of how far the charged particle has managed to spiral outwards. But if there was a physical limit, like an internal radius, how far the charged particle can actually go, and obviously it's then designed so it doesn't strike the sides, it is then guided out, as you can see in the diagram. Then that will determine, that'll be one of the features that determines how much energy you can actually get out of these. Okay, now we've got another equation, so I'm going to zoom in so I can just be careful with my writing. Okay, we've got another equation for kinetic energy that we're aware of, which is K equals half mv squared. Okay, so that's another formula for kinetic energy. Now what we're going to do is we're actually going to marry up these two equations. Okay, so we've got R equals mv on BQ. But what I'm actually going to do, I'm going to use, I'm going to rearrange that. So I'm going to write V equals, upon rearranging that, it will be BQ R on M. All right. Now, V squared equals B squared Q squared R squared on M. All right. Now, why am I doing all that? Well, I'm actually going to substitute that into here, into my formula for kinetic energy. So let's just go back. Let's just take this up here. K. It's not a very good K. Try again. So kinetic energy equals half M. Actually, I forgot there was actually a square on that M as well. My bad. I know where that would end up if I didn't put that on there. The M would be cancelled. No, mass is not cancelled in this equation. It's actually quite important. Okay. But it's actually quite interesting that mass will actually feature as, in this equation, it features as a inverted proportion, inversely proportional variable. So we'll see that in a minute. Okay, then substitute in what we just had there. So then, all right, draw a line. B squared Q squared R squared on M squared. Now you can actually cancel that with that. And then finally, this is the last derivation for this unit of work. Okay. K equals B squared Q squared R squared over 2M. Okay. So let's just take that out. So there's our derivation for, that's the last equation you actually need to derive for this unit of work, as I said. And it's an interesting one in that, okay, that's your, you can use that to determine the final kinetic energy you'll get out of a particle being accelerated. Now, consider it this way. Let's look at the features of that. You've got your magnetic field strength, B. That is, okay, B squared is proportional to K. It makes sense in a way because remember, the stronger the B, the tighter the radii of the because R is inversely proportional to B. So the stronger the magnetic field, the easier it is to turn that charged particle back around through the Ds. And that actually means it will make more passes between the Ds and pick up more kinetic energy. Obviously, more charge means every pass you'll pick up more kinetic energy. More R, more radius means there's more space to do more circles. And in this actual case, mass is actually not a feature. Its mass is more of a hindrance in this instance because, okay, mass is proportional generally to kinetic energy. But this instance, it restricts how much the radius that you get out of your magnetic field. You would it actually increases the radius, my bad. It increases the radius of the magnetic field, so thereby, with a large mass particle, you're going to get less passes between the Ds because you're going to gain, with every radius gain, yeah, you're not going to get, it's going to be harder to turn, to get tight turns on your charged particle if it has more mass. So yeah, that is the last formula. So the idea is, okay, your charged particle comes out, strikes the target, it needs to have enough energy in order to fulfill its purpose. Okay, there might be a certain amount of energy required. Some of the purposes for this is to make radioisotopes, particularly ones that are beta plus emitters for things like positron emission tomography. And nuclei don't like to interact with other nuclei. You have a strong force of repulsion between the two positive cores. So you actually have to have a large amount of energy to make nuclear events possible. So with a particular known nuclear reaction, you will have a certain amount of energy that will be required in order to penetrate into the target nucleus and then cause that nuclear reaction to happen. So if that is known, then you'll plan your cyclotron accordingly. Okay, also you can tighten up if you change the type of particles, you may need to increase the magnetic field strength or some other such thing. You also notice that the voltage itself doesn't actually feature in here. That's generally the idea of that, is if you had a small voltage, well, you'd only pick up so much kinetic energy, and thereby you'd only pick up a little bit of radius. I imagine that there's more to it than that, but at least according to these equations, the voltage doesn't actually matter. Because if you have a small voltage, you do more spins, you'd have smaller radius gains, and thereby pass between the Ds more times, picking up more voltage. So voltage itself doesn't actually feature in these equations. All right, so I think I'll leave it there, guys. And continue with your own research.